Welcome to my channel. Today's practical is under coordination chemistry, and the title of the practical is determination of hardness of water with EDTA. Determination of hardness of water with EDTA. We have different techniques of determining the hardness of water, but the method we are going to use is EDTA method or EDTA titration. Now, someone will ask, what is hardness of water? A water is said to be hard when it contains dissolved salt of magnesium and calcium, or you can also say that it contains high concentration of calcium ions and magnesium ions. One of the common property of hard water, which most of you know, is that it does not easily lather with soap. An example of hard water is seawater. Now, the water we are going to use is well water. So we are going to determine if the well water is hard or not. Now, let me say something about today's practical. Now, today's practical, we are going to perform titration, as I said earlier, and the name of the titration we are going to perform is complexometric titration. It is called complexometric because the titration involves two complexing agents that form a complex with metal ions in solution, and these two complexing agents I'm talking about are EDTA, which is our titrant, and an indicator which is called EBT indicator, and the full name of the EBT is Erichrome Black-T. Now, this EBT indicator we are using for the practical is an azodide, and it is a metal ion indicator, and it forms Chelate complexes with metal ions in solution. So when you are performing a practical, and the aim of the practical is to determine or detect the presence of metal ions, then the best indicator to use is EBT indicator. So in acid-base titration, we cannot use the EBT indicator because the purpose of doing acid-base titration is to find the concentration of a particular species. So we cannot use the EBT indicator in acid-base titration. Now, the EBT indicator is blue in color when it is free from metal ions, or when it has not come into contact with metal ions, it is blue. But as soon as it comes into contact with metal ions in solution, it changes from blue to red wine. So that is how the EBT indicator works. Now, when we come to the EDTA we are using is disodium salt of EDTA. We are using it because EDTA itself is insoluble. But in this practical, we need the soluble form of the EDTA. So we reacted some amount of sodium hydroxide with EDTA. And in theory, we know that when acid reacts with base, we produce salt. So when you react sodium hydroxide, which is a strong base, with EDTA, which is also an acid, a salt is formed. And this salt is called disodium salt, which is very soluble. That's why we are using the disodium salt of EDTA in this practical. EDTA is a ligand. When I say it's a ligand, it means it is able to form a chelate complex with metal ions in solution. So that is something brief about the EDTA. So the similarities between the EDTA and the EBT indicator is that both of them have the ability to form complexes with metal ions in solution. But when it comes to the difference between the two is that for the EBT indicator, when it is added to a solution or water which contains metal ions, it reacts with some of the metal ions in solution. It does not react with all. But when we come to the EDTA, it reacts with all the metal ions in solution. So that is the difference between the two. So let me summarize all that I've said in the tree language. I want to use the tree language because almost every tribe in Ghana understands the tree language. Nti brofo bebrebe na meka na asekyere ne se and then me ba bedi dwumedie bi na dwumedie na me ba bedi no buta bi wo meni so ye wo two ions bi a ye frɛ no calcium ion and magnesium ion. Na saa two metal ions no se wo nsuo ma emma nsuo no eye hard na ye wo buro mu nsuo bi a ye de aba lab ha mo a me ba be ye nhwehwemu na mehu se saa buro mu nsuo no containing these two metal ions. Na ye wonyema bienu bi a ebeboa anya yetunya ye saa hwehwemu saa nyema bienu disodium salt of EDTA and indicator. So saa nyema bienu na ebeboa anya na nsunsun ye eda saa nyema bienu se EBT indicator se wo de gu metal ions in solution. Na say enye metal ions ni nyina na ebe form complex no. Na say wo ye titration na wo di EDTA ni start say wo di gu nsuo no mu a EDTA ni dwuma ebe di ni say ebe form complex with all the metal ions in solution, including metal ions na edi nkan any indicator na form complex no. Nti mebe ma mfa to ho yemfa ne say burom nsuo na ewa ha no it contains metal ion trichumi na me yenti be say me ma mfa so nti de yemfa ne say burom nsuo na contain metal ions. Nti say me di indicator ni bi egu burom nsuo na me expect say nsuo color no ebe sesa from colorless to wine red. It is from colorless to wine red, and nature say metal ions na ewo nsuo na are forming a complex with the indicator. Inti na asesa aye red color. Inti asesa na ye titration na EDTA na ebe wo burette ni because eno na ye titrant no. Inti say wo burette ni ma say start say ye titration na ye release EDTA ni kakra gu yensuo na adani red ni na ebe won say EDTA no ebe form complex with metal ions na into me and form complex with the indicator wonsuo no. Metal EDTA ni be form complex with those metal ions. Afa EDTA no say eguso adigu nsuo no na ebe ye bebra ebenya ahondin bi na ahondin na ebenya no sa ahondin na so sin indicator ahondin no. Nti eba ni sa metal ions na edi nkan form complex with the indicator no EDTA ni between those metal ions na free indicator ni nchen na ne na form Chelate complex. Nti eba ni sa go say indicator na eba be free from metal ion because metal ions na e bond EDTA na ba between ni free nchen. Nti nya free pe go say nsuo ni color no ebe sesa from red to blue. And I make kasa earlier no make say indicator no if it is free from metal ions say blue. Just and the EDTA na trace metal ions na free in nchen aba be free. It nsuo ni be sesa from red to blue. Nti ye titration na ye hu say nsuo na sesa aye blue pe na trace say ye do endpoint no. That is indicator no aye free from metal ions. So we ye practical ye ba demonstrate. Sorry. So guys, this is a summary or a brief explanation of what we'll be doing today. Now I will not be doing this. I have a colleague here who will be joining me. So my colleague La, please can you come and join me here? So he is a very fine gentleman who is one of my colleagues here. He will demonstrate all that I've said in English and he is going to demonstrate for us to see. Yes, so his name is Mr. Suleiman Lab. Mr. Suleiman Lab. He is going to take us through the procedure and the things we will need for the practical.
Hello viewers. As my colleague said earlier on, I'm going to take you through the practical itself and the chemicals you need to undergo this practical. One of them is 0.02 molar EDTA and Erichrome Black-T, and you also need the hard water, and you're supposed to measure 100 ml. So it means I've already measured 100 ml of the hard water, and the apparatus you need is you need a 50 ml burette, and you also need 50 ml 100 ml measuring cylinder, then 10 ml measuring cylinder, then you have 50 ml measuring cylinder too. You also need the conical flask too, and you also need a funnel in addition. But please, I forgot to mention one chemical earlier on. That is, you in the practical to also need what? A buffer solution, and the buffer is made up of what? Ammonium chloride in ammonia. Ammonium chloride in ammonia, which is supposed to give you a pH of 10. Which is supposed to give you a pH of what? 10. Maybe in the process of preparing, we'll make sure that all this comes into what? Consideration. And so viewers, so I'll just I will proceed by taking you through the practical, and by so doing, you are supposed to fill the 0.20 molar EDTA in the burette. That is your first step, and I'm going to do that. Please just concentrate.
So guys, earlier I said that the EDTA is the titrant, so it's supposed to be in the burette. So that's what my colleague is doing. He's trying to fill the burette with an EDTA.
And please, guys, before you do that, you are supposed to, that is how titration is always done. Maybe you have to pour a small sample of the solution you are going to use to do the titration. You make sure that you use that one to wash the burette first, because maybe you don't want the solution to be contaminated. So that's why I pour small amount of the EDTA in the burette. So I'll do that. It means I'm done. Then I will now fill it up because I've now reached it with my EDTA. So it means that there's no any contaminant in the burette anymore. So I'll now fill my EDTA. So maybe someone might ask why I filled over the 0 mark. I did that because, please, if you are doing titration, because we always want it to be at the 0 mark, and not only that, you always also want the tip of the burette to be filled. So because we want that, you have to fill the burette above the 0 mark, so that in the process of draining, the tip of the burette will be filled by your solution. So please, viewers, you can see that it's now on the 0 mark. At the same time, the tip of the burette has been filled. So the reason being that the burette is 50 ml. It means that the tip of the burette, the space within the tip of the burette, is also part of the 50 ml. So when you don't do that, it means that at the end of your titration, you might be getting values, but your values might not be accurate. I use the word accurate. I didn't say it's wrong, but it might not be what? Accurate. And accuracy counts. So that is that I've done. So I've filled my burette with my 0.02 molar EDTA solution. So and the second step is that I will now measure my 100 ml of what? The hard water. 100 ml of my hard water. And as I told you earlier on, it has already been measured. My 100 ml of hard water, it has already been measured. So it means I'll just quickly pour that into my what? Conical flask. Yeah. And the next step is that I'll add 2 ml of my buffer solution that I told you earlier on. 2 ml of my buffer solution. And somebody might ask, why are you adding 2 ml of buffer solution? Please, the buffer solution is added gets to resist change of pH. Because the moment the pH changes, it means that at the end you won't get your actual endpoint. And not even that, because the metals ion in the water and the EDTA are all what? pH dependent. It means when you don't add the buffer, they can change the pH of what? Of your solution, and that at the end you might not get your actual endpoint. So it means I will now do that. As I told you the reason, it means it means now compulsory that I should add what? 2 ml of what? Of my buffer solution. And already it has been measured. You see, this is 2 ml of my buffer solution, as you can see. 2 ml of my buffer solution. So it means I'll just quickly pour it inside my conical flask. So it means my next step is now to add what? My indicator. That's the Erichrome Black-T, Erichrome Black-T. And somebody might, how many drops? I mean, I'm adding 3 drops of my Erichrome Black-T, and I'm going to do that. 3 drops. So I've added 3 drops of my Erichrome Black-T. So it means that I will now undergo the titration.
So please, when I was explaining it earlier, I said that when you add the EBT indicator and the water contains metal ions, when it reacts, you are supposed to see a red color. So this is the red color. So this means that the metal ions have formed a complex with our indicator. So that is the red color I was talking about. Okay, Mr. La, please continue.
So as my colleague was saying, it means that just be observant. As you were saying in the theoretical aspect, she told you people that when you add the Erichrome Black-T, as he said just right now, it will turn from what? The colorless solution will now turn to one red. And during the titration, it's going to be a 2-step color change. Please, and the 2-step color change is that you see, you do not turn from what? The one red to purple, and from purple to blue. So take note. During the titration, it means it's going to be a two color change. It means 2-step color change. From the one red to purple, and from purple to blue. So please, viewers, take note. So it means that when you are doing it at the place, you make sure that when you are draining the solution from the bread, please, the EDTA, you drop a little by little, because this is your first titration. It's not like it's a subsequent titration that you might know maybe the range of your what the volume that will be drained. That maybe you drain to a particular volume, and but now you don't know yet. So now you need to take your time. You drain little by little and shake.
So he's adding the EDTA to our water sample, which already contains the indicator. Yeah, so he's doing it drop by drop, because this is the first titration. So he's doing it drop by drop. And he said that we are expecting 2 color change. That is from pink to violet to blue. So we are expecting that the second color change should be purple or violet. That's what he's doing. So you can see that the red color is gradually changing. It's becoming faint. It's becoming faint. So yes.
So you can see what I was saying. So I hope you can see what I was saying.
So that's our color change, our blue color change. Yes. So at this point, it means that all the metal ions that formed complex with the indicator has been taken away by the EDTA. So now the indicator is free from metal ions. So it has returned to the initial color, which is blue. Yes, so that's the end.
Please, somebody might also ask why we didn't get the purple color. Please, in this titration, even a drop from the purple color, a drop alone can change directly to the blue color. It means that, you see, as I was doing, it got to a particular point. You see, I kept about 2 or 3 drops. So it means that in that particular range, the purple color quickly changed. It means that is why I didn't see the purple color. It means the purple color quickly changed from purple, from the one red to purple and to blue. That's why we didn't see the purple color. Well, in that range is too small. Even a half drop can change it from the purple to blue. So it means, you see that, that's what I was telling you, when you are doing this titration, you need to take, but what thing you need to note is that your endpoint is blue. The purple is only telling you that maybe when you get to the purple color, then take your time. It means a drop can change it to blue. So when you don't see the purple color, it doesn't mean your titration is wrong. No, but it's only a sign to tell you that you are nearer to the blue. So take time. So, but when you get the blue color directly, it doesn't mean you are wrong. You are right. So that is what we had. So viewers, I will now read, as my initial was 0.00, so I will now read my final volume. So it means that my final volume will now be 7.0. My final reading will be 7.0. Please, as if you are reading, you are taking, because this, if you are reading, you need to take the reading from the meniscus, and the meniscus, you see the meniscus is curved down, so you are taking the bottom. Are you getting it? So it means you can see that the bottom lies on 7. So it means your final reading will be what? 7.0. So that is the final reading. And we were supposed to do this like 3 times or 2 times, so that we get consistent values. Then we'll find the average titer. But as I did, because you can also do the second ones, it means that I will just use my 7.0 just to calculate for the rest of the calculations. Just to calculate for the rest of the calculation, that is the total hardness of the water. But if you are doing it in the lab, it means that you are supposed to do it like 3 times. 1, 2, 3. Then you take the average. So it means that is what you are supposed to do. But now, I will not show you how to calculate the total hardness, because these are theoretical things. But I was supposed to show you how you go about the normal particle. But the theoretical things, those ones are just theoretical. So those mole concepts. So you apply mole concept in calculating for the total hardness, and this is not something I think will be difficult, because I hope most of you have done mole concept since your secondary school days, even till where you are. So I don't think that will be a problem at all. So it means that on this note, I will now ask my colleague maybe to continue from where I stopped. Thank you.
Thank you, Mr. Suleiman Lab. So guys, all that I said in English and Tree, Mr. Suleiman has demonstrated for us to see. So to calculate for the total hardness, that one is theory. So you follow theory, you use the average titer, then you calculate for it. So guys, it's unfortunate we've come to the end of today's practical, and I have to say goodbye to you all. Please subscribe to my channel, Priskano Chem. The spelling of the Priskano is Priskano, and that of the Chem is Chem. Please, if you enjoyed this video, give it a thumbs up, share the link with your friends, and comment. And thank you so much for watching. You at home, thank you. And Mr. Suleiman, thank you also for demonstrating it for us. And please take care of yourself, and I will see you in my next video. Adios.